Um, so let's pick up a very small example just to understand what we are doing. So if we pick up that code, you see that code is made of two for loops, one outer loop and one inner loop, and we are just adding 3 to a variable x. So we say x is equal to x plus 3, right? This is called pseudocode because that code is not a legal C++ code or legal Java code or legal C code. It's just like some abstract language, which is very close to a programming language. So very easy to turn that code into a C++ code, of course. Now, what does this code return? Well, very easy to understand. Actually, that code is what is the value in x? At the end of the process, in x, you will find 3 times n plus 1 divided by 2. This can be proved by induction. Can be proved by induction. You see, for example, that if n is equal to 0, we don't enter the for loop because n is equal to 0. So for I equal 1 to 0, we do nothing. And so if n equals 0, the program will return 0. Okay, so which is correct because if n equal to 0, 3 times n plus 1 divided by 2 is also equal to 0. Now the induction is very easy. We assume that for k, p of k is true means if n is equal to k, at the end of the process, x is equal to 3 times k plus 1 divided by 2. Now, we do one more iteration. One more iteration will add to x 3 times k plus 1. And so the total value of x will be, after one more iteration, 3 times k plus 1 divided by 2 plus 3 times k plus 1. So you see here we use this one, this one. This one is the inductive hypothesis because we say that p of k is true, and then we had the new the new part from the last iteration. Now, if you combine this sum, you will find this one. You will find the final here, which is 3 times k plus 1 times k plus 2 divided by 2, which is p of k plus 1. And so we can prove using induction that this code is producing this value in x. Now, how long does this code run? How much time does this code is taking to run? Well, actually, that's fairly easy to compute. You see that actually, how can we count the time? Counting the time cannot be done in an accurate way. Actually, we don't know how much time is taken by like a single simple statement. If we pick up the assignment, for example, we don't know what is the time to compute an assignment. That time cannot be known because it will vary from one computer to another computer. And so those absolute values are not interesting to know. What we can say is that in that code, there are some statements which are taking some unit time, and no matter the amount of the unit time. So we see that we have, for example, as a basic statements, we have, for example, the assignment, we have the comparison, because in the for loop, when you say for I equal 1 to n, we have to compare the value of I with n. And so this is one of the basic statements we have to do. Then we have a sum. We do x plus 3, which is like a basic statement. So what we are interested in is not the value, the time of each of those statements. We want to count the number of repetition of the statement, which is more important. So here you see that actually the x assigned to 0 is done only once. Return x at the end is done only once. And so this is not really interesting in the complexity because there are only basic statements done only once. And difference is with that statement, the assignment x assigned to x plus 3 is repeated a number of times. So what we want to count is how many times we do that one, because this is the one we can repeat a lot depending on the value of n. If n is equal to 3, we don't repeat it too much. If n is equal to 1 billion, we will repeat that one a lot, right? And so what we count here is exactly the number of times we do the inner statement inside the inner for loop, because that statement we repeat most in compared to all the other. And so it's like the complexity. It's a little bit like the counting the number of repetition. And so it looks like 2 plus 2 times the number of time the inner loop runs, right? So the one you see here, right? So that 2 is for, you know, the x assigned to 0 and return x, and then the 2 times number of time is for the inner loop, right? So actually the total number of loop iteration is obviously n times n plus 1 divided by 2. Because for I equal to 1, we do only one iteration inside. For I equal 2, we do 2. So we sum up 1 plus 2 plus 3 plus 4 and plus up to n. And the sum from 1 to n is equal to n times n plus 1 divided by 2. So this is extremely common loop structure. It's good that you memorize it, because we will see that many times. And it's very easy to prove what we just said, because it's the same as before. So the number of times we do the inner statement, the statement in the inner loop, which is x assigned to x plus 3, is n times n plus 1 divided by 2. Actually, once we get that result, we don't care too much about the details of that expression. And what we like to grab is the leading term of that expression. And the leading term is n squared. And we can say something like, wow, so the complexity of this piece of code is actually proportional to n squared. What is the meaning of that is, if we run that code for a given value of n, we get some time. Then we run the same code and we double the size of n. Well, the new time will be not the double of the first time, but 4 times the first time, right? Because if you double the value of n, the complexity moved from n squared to 2n squared, which is 4n squared. We have a spatial notation we will study, which is a big O. That big O is a formal tool in math to express a proportionality, to say Well, n times n plus 9 divided by 2 is about n squared. We don't care about the small terms because they don't count too much, and so we have a spatial notation to grab the important term in the expression. Actually, to understand this concept, we can understand it practically. If you take the two functions n times n plus 1 divided by 2 and you compare it to n squared divided by 2, compare the two, well, you see the relative difference between the two is decreasing a lot very fast as the n is increasing. For small n, of course, there is a big difference, but for little n there is no difference. For big n, if n is getting bigger, like 2000 for example, the difference is very small. As the n is increasing, the difference between those two functions is extremely small. This is why we want to approximate. When we see that expression, we say the complexity is this one. Well, actually, we don't care about the details. We can say, well, actually, this is about the same as n squared. We don't care even by the divide by 2, and we will explain that in the next chapter. Actually, we can understand this using geometric interpretation. If we have this scheme, the two for loops, what do we describe is we just describe all the square you see here. Actually, the number of squares here is n power of 2, right? That's the area of the big square here. And actually, what is described in these double for loops is the squares which are yellow or orange here, which is n power of 2 divided by 2, right? And so as n is growing, the extra area compared to the lower triangle go to 0 because it's insignificant, right? That's a geometric interpretation of it. Okay, so we just introduced now on the very last slide the concept of the big O notation, and we will explain that notation in details on the next lecture. So the big O is a way to express some kind of proportionality, and it helps us to get rid of the details. So big O of log n means if a function is equal to big O of log n, it means that the function is